Hey guys, welcome to part 2 of our static electricity lessons. So we talked yesterday about kind of what charges are and where they came from, some of the history behind them. Today, we're going to look at how do we actually make these charges happen and how can we charge other objects. That's kind of our big focus for the day. So let's hop right in. We talked about, to get charges actually apart from each other, we have to separate them. So how do we do that? If we want to separate our electric charges, well, what we're actually trying to do is transfer electrons. There it is. Transfer electrons from one material to another. And we do that by rubbing them together, usually. So we just basically take the two things, smash them together, grind them across each other, and it should rub some electrons off of one and onto the other. Now, conductors, like we talked about yesterday, lose charge easily, right? The charge can fly throughout the entire conductor, go wherever it wants to go, which makes it easy to find some place to hop off, to ground itself, to neutralize. So if we want to keep something charged, we usually use insulators for generating static electricity. But can we use any insulators? Can I take any insulators at all, rub them together and get charge? Let's try it. Pause the video, take 2 sheets of paper, rub them together, try to make them spark. Go for it. What do you notice? So, gave that a shot, and you probably noticed literally nothing, right? If I grind paper together, it's not going to make any sparks. Otherwise, your binder would shock you every time you opened it. Rubbing objects together will only generate a static charge if one object can gain electrons and the other can easily lose them. Now, I got paper and I got paper. They have the same kind of urge for electrons, if you will. Neither wants to steal them more. No one piece of paper wants to steal electrons more than the other sheet of paper. So you're not going to get any kind of charge going on. Now, we call that urge to steal electrons electron affinity. And affinity just means like how much you like something, how much they like electrons. So like with our paper, if you rub 2 identical materials together, nothing happens. They have the same electron affinity. So what kind of things do work well for static electricity then? Well, scientists wanted to know that same question, so they did what they do best and lined up a whole bunch of experiments and developed a chart of electron affinity. What things really, really like electrons, we'll throw those back at the top. What things are easy to get rid of electrons, we'll throw those ones down at the bottom. And they named this chart the Triboelectric Series, which I'm not sure why they named it, but it's super fun to say. You should try it. Triboelectric Series. It's a fancy word. You drop that, everyone thinks you're super smart. So here's the deal. You pick 2 materials from opposite ends of this series. One that really, really, really wants to steal electrons and one that couldn't care less if it gives them away. Then you have the best chance to create static electricity by rubbing them together. So you Google it. Just literally Google Triboelectric Series, hit the Google Images button. This is what pops up, a whole bunch of different charts. And they'll show you what these objects are. If you look on the positive side, super positive ones that want to steal or want to give away electrons, are stuff like air and human skin and animal skin and cancer-causing asbestos. Gross. And over on the negative side, you've got like ebonite and hard rubbers, you got Teflon, you got selenium, whatever that is. All kinds of good stuff. Now, let's talk about this practically for a second here. Rubbing stuff on air, well, that's not very easy to do. You just wave it around in the air like a maniac and hope to get much of a charge. Using human skin, I don't think is ethical, so we're not going to be doing that. Leather is an option, but it's kind of expensive, and asbestos causes cancer. So the top 4 are out. So what we're probably going to use and what you find are most commonly used, glass is very common, nylon, wool, fur, and silk. These are the easiest ones to get your hands on in terms of like the ability to charge. And also not like toxic and super expensive. Over on the negative side, ebonite, also known as hard rubber, is actually pretty easy to buy. We'll often find PVC. That's the kind of pipes you use in like plumbing. You can buy that at Home Depot. Tape or saran wrap is occasionally used. Polystyrene or polyesters are very common. So is latex. And down here, neutrals, wood, steel, paper, cotton. You don't use those often because they're right in the middle. They charge a little bit, but they wouldn't be great. And obviously rubbing paper on paper didn't work because neither of them wants to give or take electrons, so you're not going to get much action there. So you've got all these different charts. Some of them are set up differently. This is a big giant list with your positive ones at the top and your negative ones at the bottom. Some of them have different things on them. Like this specifically has like rabbit fur and acetate. What else has got on here that's weird? Sealing wax, mylar, all kinds of weird things the other one doesn't have. It just depends on who made the chart and what experiments they were looking at when they actually designed it. So they'll all give you kind of the big ones. You're going to see like glass and wool and fur and lead on pretty much all of these things. But some of them will have more detail than others. Not a big deal which one you look at. So let's take a minute here to experiment with this. I want you guys to open the balloon simulator, and the website is right here on the notes. Hopefully it's attached to your Google Classroom as well. Select Show No Charges first, and then see what happens when you rub the balloon made of latex, hint, hint, on the sweater, which is made of wool, hint, hint. So grab those things, play around, and try to answer these questions. Without the charges on, just tell me what you see when you rub, what happens after you rub the balloon on the sweater? What happens when you bring the charged balloon near the sweater? What happens when you bring the charged balloon near the wall? And then predict why these things happen. Once you've done that, turn on the charges to help you check your predictions. So do these things, you'll have a spot where you can write down your answers. Here's what the balloon simulator looks like. Down at the bottom corner, show no charges. So this is where you're going to start. Grab the balloon, rub it on the sweater, and see what happens. And write about it. Pause your video, do that now. All right. Hopefully you guys paused that. You got that section done. We're going to talk now about what you just saw. The behavior of a neutral object when charged objects are nearby. So this is technically it's the reverse of what we did. We looked at a charged object with neutral objects nearby. Now we're going to look at a neutral object when a charged object is nearby. We're going to open and play around with the aluminum can polarization one. This is a PhET simulator. It's actually not from PhET. That was my mistake. It's from physicsclassroom.com. So again, hopefully this one is linked up, but here's what you're going to do. You're going to fire this thing up. You're going to turn on charges. So actually see what's going on. Bring both the negatively charged rod and the positively charged rod close to the can. What do you notice? So you should be on this physics-classroom.com/physics-interactive/static-electricity. Again, hopefully this link is posted so you don't have to type this whole thing out. But when it loads, and it's going to load soon, right? There we go. Once this thing is up and running, you're going to see there's a little button you have to press to launch the simulator. Come on, internet. See, you guys aren't the only ones with these problems. It's not the Chromebooks. It's everything. It's thinking about it. Anyways, once this loads up, there's going to be a big old button that says, like, start the simulator or something like that, or launch the interactive. Maybe it's launch the interactive? That sounds right. You're going to click on that, and it's going to launch this tiny, tiny little window. There is, in the top left corner, a little zoom in and out button. I highly recommend you push that button. It'll make it bigger. It'll full screen it, and then you can actually, like, use the whole thing. There you go. You see the button in the corner. Hasn't actually loaded yet, but you can see that there is the button in the top left corner there. But this is the simulator. Load it up. You'll notice there's a positive rod and a negative rod. You can click on them to actually get them going, which I will show you in, well, at this rate, about 35 minutes. Come on, internet. This is wild. This is slower than usual. You guys got to turn off your YouTube. You're draining all my internet. I don't want to maximize it, otherwise it's going to take even longer, maybe. I know, riveting television here, right? Or YouTube, I guess. Oh, there's a loading bar. We're making progress. Nerd Island Studios. See, that's where I would go to vacation. Nerd Island. Sounds lovely. It's even got a nice little tree on it. So it loads up, does its thing. Hopefully yours is a lot shorter than mine is. Okay, really? You're going to freeze at 80% here. There we go. Bottom center, show charges. You click on that. And you see the charges pop up. And you'll notice that the negatives and the positives are all kind of stacked on top of each other because positives and negatives attract. You got a glass rod or you got a rubber rod. You could pick. Click on them to make them show up, and then you can drag them around and see what happens. I'm not going to spoil the fun and give away all my secrets here, but that's what you're supposed to do. Pause it now, play around with it, answer the questions on your notes. All right, so let's general observations. What did we notice so far? When we're talking about the balloon and the sweater, well, it was charged up, and it was attracted to both the wall and the sweater, which are both insulators. It's a little weird, right? It's being attracted to insulators. That kind of makes sense, I guess. But the aluminum can, and aluminum's a metal, it's a conductor. It was attracted to both a positive and negative charge as well. So it doesn't matter if you are a conductor or an insulator, neutral stuff is attracted to charged stuff, no matter what the nature of those objects are. So if a neutral conductor and a neutral insulator are both attracted to charged objects, what's going on? I thought they acted differently. Well, we can explain it, but their attraction, why they're attracted, is explained a little differently. When a charged object is brought towards a neutral conductor, the object is attracted due to charge separation. The charges separate by some distance, which makes the different ends different. So we're going to call this a negatively charged box. And I bring this near a neutral conductor. If it is negatively charged, it's going to repel negative charges. So all the negative charges that are in my conductor are going to repel away to one end, whereas my positive charges stay fixed. And so what ends up happening is your conductor, the charges separate. All the negatives go to one side. You end up with a positive end and a negative end. And hey, look at that. Positive, negative, positives and negatives attract. You have the attraction of a conductor to the insulator, or to the charged object. So that's how conductors attract. That's important. The conductor is attracted by charge separation. Now, what about a neutral insulator? A neutral insulator. Well, this object's still attracted, but it's called charge polarization. Let's use the same thing. We'll do it negatively charged. You can do it with positive charges as well. You just get the opposite kind of effect here. So, this is now my insulator. So what ends up happening in an insulator is if you were to picture your atom, positive charge center, electrons are on the outside. Well, if I bring a negative charge close to this atom, I end up with a charge center and all my electrons on the far side. They repel. They can't escape. They can't move to the far side because they're stuck there. But you end up with positive charges with your negatives all pointing the same direction. So your negatives act almost like a magnet and they point a certain direction. The negatives repel away. They don't cluster. They don't separate. They do what's called polarization. They kind of spin. So all the negatives are as far as possible as they can get without actually separating. So you end up with a slightly positive end and a slightly negative end because the charges have flipped like a magnet to point in a certain direction. So they align opposite to one another, but they're actually not that far apart. But because they're all pointed in one way, it acts like a magnet, and you have a positive attracted to a negative again. So the insulator is still attracted, but the charges don't actually separate like they do with a conductor. So it looks the exact same to us, but the actual action is different, and that's because of the fact that electrons can't move very easily in an insulator, but they move just fine in a conductor. So what happens if we bring two neutral objects together? Go for it. Grab a couple neutral objects, a couple more pieces of paper. Put them right beside each other. Do they attract or repel? I'm going to pause here, give you guys a second to do that. Now, I mean, this wasn't a trick question, but maybe it was a bit of a trick question. They don't attract and they don't repel. What happens to them? Big old pile of nothing. Nothing happens. This is actually proof neutral is not a third kind of charge. If it was, the neutral object would repel, right? Because like charges repel. So these can't have the same charge. Otherwise, they'd repel from each other, and instead, they just sit there, exceptionally boring. So they are not a third kind of charge. It is a balance of charge. Nothing happens. A neutral object has the same number of positives and negatives. That's all it is. It's not a third type of charge. It's a balance of charge. So let's talk about charging now. We can rub stuff, right? That's how we get some things charged. How do I move that charge around? How can I use it to charge other things? Well, there's two ways. The first is charging by conduction. Charging an object by conduction happens when charges are transferred due to contact. When you touch, things jump. So for example, if I had a glass or a PVC rod touching a pith ball. Okay, let's explain this. Here's a charged rod. Let's make it positive. All right. A pith ball is a little tiny conductive ball that is really, really, really light. It's light and it's conductive, which means it can move really easily. Now, it's neutral. It's going to be attracted to this little charged rod. And what's going to happen? Well, the rod's positive. So any negative charges that are on the ball, even though it's neutral, are going to get, all those electrons are going to get sucked into the rod, which means the ball will be left, what charge? If I take away the electrons, the ball ends up slightly positive. And so because the ball is now positive, and even though the rod soaked up a couple of electrons, the rod is way bigger, so it's still going to be positive. You'll find that what ends up happening is, in step 2, our positive rod repels the pith ball. So it gets sucked towards the rod, and then it touches and transfers charge by conduction. The electrons touch and jumped into the rod, and then the ball will repel because it's now positively charged as well. So note that when an object is charged by conduction, the charge on both objects is the same. Positive rod, positive ball. If I had a negative rod, it would do the opposite. It would push electrons onto the pith ball. Negative rod would make negative ball. Now those electrons aren't gone, just to remind you, they're inside the rod somewhere, but because the rod is so big, the electrons don't make enough of a difference to neutralize it. The rod would be very slightly less positive. Let's put it that way. So let's draw some drawings here. Let's try this. Illustrate what occurs when a positively charged acetate rod, so we got a positive rod, is brought towards the ball and they touch. So, neutral ball. That's step 1. That's when they are far apart. Step 2. Let's bring them close together. Well, now I've got a charged object that's going to be attracted as the charges separate. The negatives go to one side, whereas the positives stay still. So that is a conductor, so the charges separate. All right. Now they're going to touch. There's my ball. Now the the positives are still there, but my electrons have jumped into the positive rod and basically disappear. They're eaten up by the positive. There's so much positive on that rod that the charges disappear. So finally, after they have touched, you have a very positive rod with, it's still got the negatives in there somewhere, but you can't really see them. And you've got a positive ball, which still has its positive charges because they don't move anywhere. And because they're both positive, like charges repel, and that ball gets pushed away. So you'd see it attract, you'd see it touch, attract, touch, repel. That's the series you would see. So you guys could trace this out in like Paint or something if you wanted, and then copy paste it into your notes might be the best way to do it. Or if you have a printed out copy, you could always hand draw it. Or if you have a drawing tablet or something fancy like that. I mean, you guys have touch screens. You could figure this out. You're smart people. Pause it if you need. Find a way to jot these diagrams down. And now that you know how to draw stuff, we're going to draw another set of things. But this time, not a positive rod. I want you guys to see what it looks like with a negative rod. Negatively charged rod. Pith ball. They're far apart. Not much is going to happen. So I bring them close together. Negative rod. Inside my ball now, I got the same positive charges, but the negatives repel. Because, of course, like repels, and those are both conductors. But if you look now, you've got a positive side and a negative side. They're going to start attracting each other. Step 3, they're touching. So you have a slightly positive ball. All the negatives are on the far side. This rod was filled with negatives. So what's being attracted to what here? Well, the negative charge from the rod is being attracted to the positive charge from the pith ball. And so you're going to get a couple more negatives in there. A couple negatives are going to transfer. The rod will become slightly less negative. But again, that rod's got a boatload of negative charge. It can afford to give up a couple, and it'll still be negative when it's done. What's left with the pith ball? Well, now it's got a bunch of negative charge. It's got way more negatives than positives. It didn't actually grow bigger. I'm just a terrible drawer. And so now, even though you have negatives repelling, it's got so many negatives that the whole ball gets repelled. And you end up with a negative charge on the rod and a negative charge on the ball. So it works with positive or it works with negative. If you touch them, they both end up with the same charge and they end up repelling, and it looks the exact same. But can we charge without direct contact? Well, we can charge by induction, which is kind of cool. You still need to touch it, but you're not touching it with a charged object. Let's talk about that here. You can permanently charge something neutral without touching the object with a second charged object through a process called induction. Now, here's the basic diagram of it. We're going to step through all this and draw it. It just won't be not nearly as nice as this because, well, you've seen my artwork. Basically, you got two metal spheres, two conductors, that are sitting on insulating stands, so electricity can't run down to the ground. I bring a charged object close, so it's not touching. Notice the gap here? Not touching. And it repels all of the, well, not all, but a lot of the electrons from sphere A over into sphere B. Then all I have to do is separate A from B so the electrons can't go back. If I take away the charged object, I haven't actually touched anything with that charged object yet, but I've used it to push electrons from A to B. You end up with B being more negative and A being more positive. You have tricked it into being charged. And it works with positives too. If I bring a positively charged object towards a neutral object that's a conductor, the charges separate with the negative electrons closest to the charged object. So if I've got two things touching and a big positive charge, all my electrons are going to swarm over here. So my electrons all get pulled towards the positive charge. If I were to touch a neutral object with a ground when the charges are separated, now here's the tricky part. I use my finger or a wire and I connect this to the ground. It's positively charged. So what does the ground want to do? Well, ground is going to try and neutralize it. It's going to swing some electrons up here until this is neutral. Cool. We take the ground away afterwards. Actually, I'll just... Can I drag that and move it? There we go. We take the ground away afterwards, which means those electrons go... I'm not going to move them all because it's going to take forever, but you get the point. So now I have a lot of negatives on that thing that I just put together. If I take away the positive charge, well, what's going to happen? Take away the positive charge, the electrons all go back to balanced on this object. But if I were to count my electrons, I would have way more electrons than I did before. So even though they're evenly spread out, I would be using a positively charged object to create a negatively charged object. I don't even have to pull those spheres apart to make that happen. Take a look at this one. I used a negatively charged object to create a positively charged object here. So whereas with conduction, whatever you touch, that's the charge you get. With induction, you actually form the opposite charge. So what would that look like for a negatively charged rod? You know what? You guess. I'll draw it out in a minute, but I want you guys to pause here and actually give this a shot. Try and sketch out what would happen with a negatively charged rod. Let's do it. Negatively charged rod, which means, let's do it with the actual count here. 1, 2, 3 positives. I'm going to give it 3 negatives. They're going to get repelled. Right? Like charges repel, so it's going to repel. I'm not even going to use 2. I'm just going to use 1, and you'll see that this works. Step 2. I hook up my grounding wire. This should actually be touching. There's my grounding wire. And so where do the electrons go if they're being repelled? Oh. No, I want this one. It goes down the wire. It repels right out of the object. No, give me the electron. Yeah. So they would repel right down the object and out. So then I say, okay, let's take my grounding wire and move it. And then let's take my rod and move it away. What am I left with? My negative rod has created a positive object. It pushed the electrons out and into the ground. So those electrons are over in the ground somewhere now. They're soaked up by the earth. And so that object left is positive. Now I want you guys to practice with this a little bit. Well, it's not really a quiz. It's more of like an interactive activity thing, but take the quiz at the following link. Screenshot your results when you've answered them all correctly. When you get it right, you should get a little star beside it. When you've got all your stars, it'll give you a little like certificate of completion or something at the end. Give it a shot. So again, hopefully this link is posted in your Google Classroom. If not, it is real easy to type. It's just www.physicsclassroom.com/physics-interactive/static-electricity/name-that-charge/name-that-charge-interactive. How hard's that, right, guys? So hopefully I posted to Google Classroom. If not, you can copy it from here and type it in. It should look like, and I guarantee this is not going to load on the first try. Oh, that was fast. It should look like this. And when you're done, this is, I did it already. I didn't want to spoil the questions. So this is what that little certificate thing I was telling you about would look like. Name that charge. You have done it. You have successfully analyzed each of the 7 situations. You are the champion of charge. And then your name can be in there. So make sure your name is in it. Screenshot that and send that into your teacher in whatever way, shape, or form they like. And you should be good to go. Boom. All of you are going to be champions of charge. Come on, load. That was supposed to be impressive. There it is. All of you are going to be champions of charge. Thanks for watching, guys, and I will see you guys next time.